Today we'll cover one of the more mind-bending and complex aspects of physics. We'll be covering the postulates of special relativity and a couple of the problems and concepts that will eventually lead to what are called time dilation and length contraction. But first things first, we have to set up a foundation on Einstein's postulates of special relativity. Keep in mind that this is called special relativity because these two postulates only really apply in special cases where an object is going a significant fraction of the speed of light. Einstein's first postulate of special relativity sets the base of relativity in general. The first postulate being, in essence, that depending on your motion, you see things differently. For example, if you're in an airplane taking off from the airport and you watch out the window, the ground will appear to fall out from under you. Well, if you have a friend who's watching your plane fly away, to them, the plane is moving onward and upward away from the ground. There's two different ways to view in that situation. And so it really all depends on where you're standing. Einstein's first postulate also states that physics are most easily measured and most widely applicable when objects are in what are called inertial states of motion. That is, being motionless or moving perfectly straight at a perfectly constant speed. Take the plane example we used earlier. If the plane has a perfectly straight course and is moving at the same speed, while your friend is standing still at the airport, you can use around the same set of equations to find any value you're asked in relation to either the friend or to you in the airplane. The second postulate, as laid out by Einstein, shows that there's a universal speed limit of sorts. And that speed limit is the speed of light. All right, so as you can see, here's the equation for time dilation. It has a huge factor in it played by the speed of light, as you can see right here. So this little bottom piece of the equation is really important because if your velocity squared ends up being greater than c squared, then it'll be 1 minus some number bigger than 1. That will make it so the overall equation is negative, and instead of slowing down time or changing how time functions like you do when you get close to the speed of light, you'll actually start going backwards in time. The speed limit for going forward is therefore the speed of light. With that universal speed limit comes some restrictions on the properties of light, namely that when you're dealing with relativistic speeds and the motion of light emitted from an object, the motion of the object and light, that speed of light, will not add. But instead, the light emitted remains at the speed of light. No matter what, if light's emitted anywhere, anytime, in a vacuum, it goes more or less 3e to the 8 meters per second. An example of this is how we view stars and the expansion of our universe. If a star is moving towards us at half the speed of light and emitting light at the speed of light, we don't see the light from the star moving at 1.5 times the speed of light. Instead, we see the light moving at us still at the same speed, but with a couple different properties that we won't talk about that help us understand that it's coming towards us. All right, with the basis of special relativity out of the way, we can get into some of the phenomenon it presents us. Because this is relativity, it will get pretty weird, but we'll go more into depth of each of these phenomena in just a second. But just as a brief overview, the overarching concept for time dilation is that the faster you move, up to the speed of light, of course, the slower time will go according to your frame of reference. The overall concept for length contraction is that as you move faster, the length of the object that is moving fast will seem shorter from the frame of reference of an observer outside the object. Likewise, the distance traveled will seem to be shorter according to an observer whose frame of reference is with or within the object traveling relativistic speeds. A simpler way to think about this, though the concepts don't apply as well, is the length of lines on the freeway. If you walk past them, they're several feet in length. But when you're going past them at freeway speeds, they only seem to be inches long. Because of the two postulates that we just talked about, the two consequences of Einstein's special relativity postulates, we encounter something called simultaneity, meaning that events that seem simultaneous at one reference frame may not for another frame of reference. For example, if you have a spaceship going at half the speed of light, and two lights, one at the very front and one at the very back, turn on at the same time, and if you're in the spaceship, you'll see the front one turn on first because you're moving that direction and that light's coming towards you. And even though they turn on at the same time, and you'll see the back one second. However, your friend at a different frame of reference will see them turn on at the exact same time. So the way things happen, according to special relativity, is all depending on where you are. So here's our example for time dilation. The spaceship on a new route from Earth to Mars, which is approximately 25 billion meters, traveling at 1/3 the speed of light, according to an observer on Earth. A round trip for this rocket takes 75 minutes. So let's use the equation for time dilation to figure out how long that same trip takes according to the pilot of the rocket. So looking at this equation, this is the one we're going to use. So T prime, this little T apostrophe, is the time measured from an observer outside the frame of reference. That's our 75 minutes. T is what we're trying to find, and then the square root of 1 minus velocity, or 0.3 meters per second, divided by, or not 0.3 meters per second, 0.3 times the speed of light, while c is the speed of light itself. So let's plug it in and see what we get. C prime equals t divided by the square root of 1 minus v squared divided by c squared. There we go. So 75 equals t, it's a garbage t, but that's fine, divided by the square root of 1 minus 0.3c divided by, that's squared, of course, 1c squared. And then, all right, multiply by the bottom factor on both sides, and you get 75 times the square root of 1 . And you get 1 minus 0.3 squared, or 1c squared equals t. And if you do the math out, t ends up equaling more or less 71.54 minutes. So by using this equation, by going 1/3 of the speed of light, like this rocket ship does, the pilot experiences 4 less minutes than he would by just traveling there at some non-relativistic speed. This is because there's a lot of ways to keep time, but the one we'll talk about right now is called a light clock. So light clocks consist of a beam of light, ignore my garbage flashlight, shining a ray of light at a mirror. So that light usually just travels right down and then right back. When you start going significant portions of the speed of light, that light not only now has the exact same vertical component to travel, but it has a horizontal component added, and it starts to look like a triangle from the beginning point to the end point. And so because of that, this total distance, this hypotenuse, or not hypotenuse, these two sides are longer than just this vertical side, meaning that it takes a shorter amount of time because this light clock will click less times, because instead of going up and down, it goes right and up, and then right and up. Awesome, now on to the length contraction. So we're gonna use the same spaceship and really the same just about everything else. But if we look at the equation, V times T equals D. So we know for relativistic equations that V is always constant, it's the speed of light, but time will differ depending on your frame of reference. And so because the only thing that can differ on the other side of the equal sign is the distance, and because our speed is constant, our distance will actually vary as well. It will be shorter as you get faster. We use the same spaceship as before, but this time we'll see how much the ship shrinks when it's going its maximum speed of 0.3 c. The ship, according to the pilot, is 100 meters long, but the Earthbound observer says something very different. So let's see exactly what they say and figure this out. So we have L prime, which is the measured from an observer outside the frame of reference. That's what we want to find. L is the length that the pilot says, so 100 meters. And then that same factor we had before of the square root 1 minus v squared over c squared. So let's do this really quickly. So L prime equals 100 meters times the square root of 1 minus 0.3 c divided by 1 c, and that's all squared. And so you plug that in, and you get that according to the Earthbound observer, who's stationary, of course, you get 95.39 meters. So the ship has shrunk 4.61 meters, which is a lot. It's like 20, 30 feet. You can see by those equations that it really does matter how fast you're going. So that's all for this video, but hopefully you've seen how special relativity really makes everything weirder than you could ever imagine.